What do we mean by classic petroleum system? Petroleum system, as we have learned from the oil and gas industry, is one in which the fluids are buoyancy driven. They are produced at depth and then migrate up to reservoirs and stratify with gas at the top, oil in between, and water on the bottom. The main properties of these petroleum systems is that the fluids are mobile and they accumulate in reservoirs. They are laterally extended and they are associated with horizontal reflectors. And these are properties which the oil industry is very familiar with. Gas hydrates are very different. For gas hydrates, the accumulation is determined by gas availability, and the hydrate, once it is formed, stays put. It has no opportunity to migrate into reservoirs. So the big question is, how does gas get into the gas hydrate stability zone when you would expect it to freeze at the base of the gas hydrate stability zone and have no possibility for actually filling up a reservoir? There have been a number of publications on this subject, and this is a very graphic example that was published in the Leading Edge in July of 2002. This is Blake Ridge, which is on the off the east coast of the United States, which is a quiescent passive margin. The stratigraphy is very horizontal, as you can see in the seismic section. Despite the fact that there is very little gas production in this area, you can see that there are gas chimneys where gas has broken through the base of gas hydrate stability, and there is actually free gas in the gas hydrate stability zone. Now this gas is out of thermodynamic equilibrium with its surroundings, but nonetheless is moving fast enough that it remains in free gas state at least halfway up into the gas hydrate stability zone. This suggests that if hydrate forms, it doesn't fill up the gas hydrate stability zone uniformly, but it forms as dikes which follow the path of gas seeps up into the gas hydrate stability zone, where it freezes when it combines with cold water at high pressure. So this cartoon shows what one might expect a gas hydrate reservoir to look like. At the base of gas hydrate stability, there might be a thin layer of disseminated hydrate which traps free gas, and that gives you a very strong seismic reflector, which is the famous bottom simulating reflector. However, most of the hydrate is found in steeply dipping dikes, which can stretch all the way from the base of gas hydrate stability to the seafloor. These dikes are of unknown thickness, but they might be quite narrow, and they will be and they're possibly crisscrossing because gas breaks through according to the Moore-Coulomb law. Now let's look at some evidence for this model. This is a well log from the east coast of India. This was a very successful gas hydrate drilling campaign conducted by the government of India. In track 1, we have resistivity logs, and you can see that resistivity is quite high, above 100 ohm meters, particularly at the top, and a little bit less toward the middle of the section. At the top, we seem to have a very high grade, high saturation of gas hydrate, and in the middle section, a slightly lower amount of gas hydrate. At the bottom, we have the native rock, which is below the base of gas hydrate stability. Now, this was analyzed, the image from the FMI was analyzed using dip meter software, and you can see that although the country dips in this area are known to be almost flat, the gas hydrate has dips as high as 60, 70, and 80 degrees. It appears that we have actually drilled down dikes in this vertical well. This is a cartoon of what we believe this site looks like. It is above a topographic high, a more deeply lying intrusion, and that creates a zone of weakness in the unconsolidated seafloor sediments above it. In this zone of weakness, gas will find easy paths up through the gas hydrate stability zone to the seafloor, and these paths will be steeply dipping. There are other examples of this sort of topography, subsea floor topography, notably Alaminos Canyon 818 and Mississippi Canyon 118, which are also well-known gas hydrate sites in the Gulf of Mexico. Here's another example of steeply dipping hydrate dikes in relatively flat seafloor sediments. Here, this is in Keithley Canyon 151 in the Gulf of Mexico. This was a result of the Chevron DOE Joint Industry Project. At the bottom of the section, we have relatively flat country dips of about 20 or 25 degrees. When we get up into the gas hydrate stability zone, and we're looking at the gas hydrate, which is coated white on the GVR log, you can see that the dips are well in excess of 60 degrees. That's yet another example of how gas hydrate appears to have dips much larger than the surrounding sediment dips. Here's a polar diagram of how those dips are arranged. You can see that they are this represents an azimuth and dip angle, and you can see that the azimuths are 180 degrees apart, showing a crisscrossing dike pattern which is characteristic of Moore Coulomb faulting. The maximum horizontal stress, as determined by the local geology, is perpendicular to the direction of the dikes as expected from geomechanics. And here this shows the local geology, and the drill site is right at the crest of a ridge. The maximum horizontal stress direction is along the ridge line. The minimum stress direction is perpendicular to it, and the dips are also perpendicular. There are several publications available that express this theory in more detail, as shown on the screen and available from me. And thank you very much for your attention.